Okay. Good morning, everyone. So today we are going to finish the first part of the course that is about hardware components, first block, second block, the other components of the computer, and then we have seen milestones, so the evolution of computers in history, and also the computer typologies, so embedded computers, disposable computers, and so on. Last time we have seen the mainframe, okay, mainframe, very large room size computers, okay, that recall the computers developed in 60s, 70s, very huge computer, with a very huge and high computational power. And we have seen many usages, okay, of mainframe. So we have seen that, okay, some of them are not specified since they are usually secret. They are kept secret by states. But mainframe are also used by finance, in the finance field, services. Unipo services are based on the Cineca mainframe. Okay, we have discussed about the Cineca, the existence of the Cineca mainframe. We use, as researchers, also mainframe for research purposes to try and develop data models that use a huge amount of data, maybe with deep learning procedures and so on, geophysics, and many other services that you can find here. Last time we have missed this slide is just about a focus on the main uses of mainframe. Remember that mainframes are developed for large-scale transactions, okay, processing. So we have multiple transactions on the mainframe. We have multiple users, in particular thousands or also million of different thousand, but also million of different users. So mainframes have to support programs that run in a concurrent way. So since we have many users, then we have many programs on the mainframe. And we can have many programs since we have a huge computational power. So the mainframe is able to run multiple programs, okay? So usually we have a very large RAM memory that store a lot of different programs that we can run on the same time, since we have a very powerful CPU on the mainframe, or better, in other words, multiple CPUs, distributed CPUs, and that we can use to run different programs. We have usually a mainframe is connected to a database or one or more databases. Okay, storage application, we can see in which there are all the data, in which we have terabytes of information, not gigabytes, but usually terabytes of information. So a very huge amount of data. And also remember, usually mainframes are connected through the internet network. So for the users, but also with the services. So usually they have to have the ability to handle large bandwidth communication. Here you can see other three key features about mainframe. The first is security. Okay. So we have many users, multiple users on mainframe, so data can be shared, but we can share data on the same mainframe, but we have to protect these critical data. Imagine, for example, a nation, a state that has very important services on a specific mainframe. Okay. The scope, the ability of computer programmers is also to protect this data on the mainframe. And for example, here you can see customer lists. For a company, it's extremely important to protect customer lists, okay, but also accounting data for bank, for example, employee information, and so on. Then we have scalability. Okay, the scalability is the ability to add, for example, computational power without the disruption of normal business procedures, processes on the mainframe. So we can improve, for example, we can add another database, we can improve the computational power of the mainframe without stopping the other services. This is the scalability, one of the definition of scalability. And then we have continuum compatibility. You have to imagine that usually mainframe customers invest a lot of money in developing application services for mainframe, but also to buy a new mainframe. So that's why some applications have been developed for the mainframe and refined over decades. We used the same mainframe for maybe 1, 2, 3 decades, okay, a long, very long period. With respect, for example, your laptop, that maybe use your personal laptop for, I don't know, 5 years, 10 years at the maximum. For a mainframe, we have, for example, a period use of, I don't know, 10 years, 20 years, 30 years. So the range limit, the time range is different. So the ability of an application that run on the mainframe to work in the system, also with other devices or program, is called compatibility. Okay, so we have programs that can run for a long time range on the same mainframe, even if this mainframe is updated, is changed, and so on. Okay, this is the slide about Cineca, and we have seen together what is Cineca. Is a mainframe, okay, that we have here in Italy. In particular, has been established in 1969 in Casalecchio di Reno, Bologna, that is very close to here. And you can see the building of Cineca from the highway, for example. Here you can see the specification, technical specs of the Marconi 100. The old machine, the old mainframe inside Cineca. Now we have Leonardo, is a new machine, more powerful than Marconi 100, Marconi 100. Here are the Google Maps about the Cineca, the position of the Cineca. And here the last slide about the first part of the course. So we have seen the different generation of computers, the evolution, the historical evolution of computers. So what's about today? What we can say about the evolution of computers in current time? We can say, first point, invisible computers, the IoT paradigm, Internet of Things paradigm, is changing the world, not only the IT world, not only the computer science world, but many other worlds, many other fields related to technology. Smartphones in particular have introduced a real revolution, not only a technological revolution, but also an economic revolution, and a revolution about the services provided through the internet connection, the health monitoring, for example, and many other revolutions introduced by the use of smartphone. Smartwatches that improve the paradigm of invisible computer, the 5th generation that we have seen together, okay, invisible computer. One of the example of invisible computer is represented by the smartwatches. Since we have a smartwatch or a watch in which inside there is a computer, a proper computer, there is a CPU, there is a RAM memory, there is also a ROM memory, there is hard disk, limited in size, but there is also an hard disk. And then we can use this computer inside the watch to create a smart watch, okay, that is able to compute data, acquire data, compute data, and also connect to the internet and transfer many information about, for example, your health. We can use smartwatch to monitor your health. One of the greatest revolution related to smartwatches. So smartphones, smartwatches, last evolution of personal computer. What about personal computer? Last evolution is represented by the so-called all-in-one laptop. Okay, maybe you have an all-in-one laptop here. No, I don't see anyone. So here you can see an image in which the laptop is on the edge between tablets and personal computers, okay? And we have some features from smartphone. For example, here, usually with all-in-one laptop, we have the touchscreen technology that enable natural user interface. And maybe you remember the evolution of user interface. The last evolution is represented by natural user interface. We use our body to connect, to interact with the computer. We can use the touchscreen technology to interact with the computer with our finger. Then here we have lightweight. We have long batteries, since features about all-in-one laptop is the portability. So we can the mobility also of this kind of feature devices, since we have long batteries that so we can use these devices without the plug-in of the car. And remember also the last evolution about the operating system that we have seen together about the Chrome OS, if you remember. The thing is that the computation power is less important, okay? Since we can run a lot of the apps, a lot of services are run on the web through the cloud paradigm, okay? So remember, we have a reduced or a limited computational power. Thanks to the limited computational power, we can have batteries that last longer than the other. Since we can use the cloud paradigm to have services, applications, and many other things on our computers. And that's all. Okay. So with this slide, we have finished the first part of the course, and we are entering today in the second part of the course. Okay, that is related to math. So be aware that we are doing some math today. Very limited math. It's not so difficult. Do you have questions about this part? No. Okay, so we can go in the second part. So digital representation. As you can see here, 2.1. We are in the second part of the course. Okay, so we have finished the introduction to the computer architectures. So we have seen together the working knowledge of the key terms. Remember software, hardware, firmware, operating system, and so on. The architecture of computers, the organization, all the components, and so on. And also the evolution of computer, the milestone, the so-called milestone in the computer evolution, history evolution. Now we are going to focus on the digital representation. So how is possible to use the digital representation? And we are going to see what is the meaning of digital in this case, to use computers, okay? So how is possible to use logic circuits and also the Boolean algebra? We are going to introduce a new kind of algebra called Boolean algebra. How is possible to use logic circuits, Boolean algebra to create smart computer, to create computers that are able to use digital signals to create information, okay, to process data, to create output. And also we are going to see what is an integrated circuit, also called IC or chip, and the production of integrated circuit. That is very important, okay? So also today is a very important paradigm, the integrated circuit production. Maybe you have heard something about the technological war, we can say, between different countries for the production of integrated circuits. Okay, and this is the last part that we are going to see in the last part of the course. So, first element to introduce the difference between digital and analog signals. Okay, very important difference. With analog signals, we are in the realm of continuous. Okay? We have continuous values. With analog signals, the meaning is that we have an infinite set of values. in our life, we live in analog world, since we can perceive an infinite number of colors through our eyes. We can hear an infinite number of tones. We can smell an infinite number of smells, and so on. So here in our daily life, we live in the analog world. While digital signals are in the realm of discrete. So there is only a limited set of values for these digital signals. An example, a graphical example of analog and the difference between analog and digital signals is reported here. On your left, you can see a time versus voltage graph. The meaning is on the X, we have the time. On the Y, we have the volts, okay? The voltage, but it's not important for us. We have two different units. We have an analog signal, so you can see that with this signal, we have a limited range. The range is start from minus 120 volts plus 120. Okay, this is a limited range, but in this specific range, we have an infinite number of possible values within that range. While in the digital world, we have the same graph, okay? Time versus voltage, time here, voltage here. Also in this case, we have a specific range from 0 to 5, okay? It's a different range, but it's the same thing. So we have a specific range, in this case, from 0 to 5. The difference, maybe you are able to see it, the difference is that in this graph, we have only a finite set of possible values. In particular, the possible values are only two, 5 or 0. 5, 0, 5, 0, and so on. Here we have an infinite set of values. Here only two, 5, 0. Why it's important to introduce digital signals? Since in computers we use digital signals. That's why we introduced the digital signal. Okay. In particular, in computers we use binary digital signals, in which we have only two values: 0, 1, on, off, 0, 1. The bit of information. Okay. The base unit of information, the bit, is related to the nature of the binary digital signal, in which we have 0 and 1. Okay, on, off, and so on. Okay, this is only a slide to tell you that you don't be fooled by the whole shape. Maybe you can see this graph, and this graph recalls the shape of the previous one in the analog world. But in this case, if you zoom in and you see that these digital waves is step, square, and discrete, we are in presence of a discrete signal, or in other words, of a digital signal. As you can see here, we have only a limited amount of possible values in our graph. Okay, so you don't have to look the whole shape of the graph, but you have to look the possible values that we can have in a graph or in our function. So here we recall on a slide that we have seen in the first part of the course. So how is possible to talk, or maybe to insert programs or to program a computer? We have to use the machine code, if you remember, okay? It's very important, it's mandatory to use the machine code. And if you remember, the machine code is composed by only 0 and 1s, okay? So what we can say, the machine language that we use to communicate with the computer is a binary digital signal, or only a digital signal, since we have only two different values, 0 and 1, okay? So we are close the circle. Digital signal, computer, machine language, only 0, 1. So the machine language is a digital signal. Is another slide that recalls the previous one in the first part, okay? We have seen that usually we use human programmers, usually use easier languages, LN, okay, L1, L2, L3, LN, that are translated in lower level languages. Maybe we are using an high level language, such as, for example, Java, C, Python, Fortran is not, okay, various high level languages. We translate these languages in the assembly language, the first language that use mnemonics. Maybe you remember something about the importance of assembly language. And then the assembly language is translated in the machine language, composed by only 0 and 1. That is really hard to be used since it's not easy to understand the meaning and the behavior of this piece of code. So it's important, very important, that to define what is the binary representation. The binary representation is the representation used in the machine language, and how is possible to use this binary representation to what? To do what? To, for example, make calculation, to represent numbers, to do arithmetic operation, and many other, to open an image, to show an image, to play a video game, and so on, okay? How is possible to use the machine language to do, for example, arithmetic operation done in the CPU by the who of you? Perfect. The arithmetic logic unit. We can use the arithmetic logic unit to perform arithmetical and logical operation. But to use this unit, we have to use the machine language. Okay, we have to insert in the computer the machine language that use a binary representation. And so it's important that we understand how it's possible to use the binary representation to use the computer. Okay, and this is the topic of the all following slides. Questions? Have you understood something?
Question about this.
Yeah.
It was developed a long time ago to solve the problem of using machine language. But it's an evolving languages, or it's the same?
It's an
evolving languages, or it's the same as it was first developed?
No, it's an evolving language since maybe not so evolved with respect to the other programming languages, but also we update the assembly language to match the, for example, new components on hardware. So we have a new CPU, so we have to program we have to create a new assembly language. Maybe we find new operation, more efficient operation with assembly language, and so on. So there is also research work on the assembly language. Okay. Other questions? Okay. If you don't have question, we can start with the positional representation. The introduction to the binary representation. Okay. Have you ever heard the positional representation, the word positional representation? No. This is your first time? Perfect. No problem. Okay. Remember, first point, everything inside the computer is represented using digital signals. Okay. Using a digital signal that can assume only two binary values, 0 and 1. Okay, easy. Why 0 and 1? We have also introduced this element in the previous slide, but we can repeat here. 0 and 1 suits very well with the electricity since corresponds to two states of the electric circuits. 0, 1, on or off, 0, 1, on. Okay. And the second element is that you can see every computer in a very simple way, but we can see every computer has a huge set of different switches. switches that can have two different states, on, off, 0 and 1. That's why we use the binary representation, since we only use the two values that can be used by the switches. Okay. What are these switches? Remember, vacuum tubes, relay, and nowadays transistors. Okay. We have different technology, but the same behavior. A switch can be on or can be off. In the binary representation, again, the basic information unit, 0 or 1, is called bit. Okay, so a single bit can have two values, or 0 or 1. And then we can introduce this terminology. We have a byte of information when we have a sequence of 8 different bits. Okay. If we have 8 bits, we can say, okay, we have a 8 bit of information, or we have 1 byte of information. It's the same thing. Usually we use the word byte. It's more easier. It's more easy. Why we use the term bit? For the internal parallelism of the CPU. Okay, so remember this difference in the usage of bit and byte. The word is a sequence of 16 bits. Unfortunately, we use the same word for a sequence of 16 bits, but also we use the word to define the internal parallelism of the CPU. Okay, sorry for that, it's not my fault, but we use the same word. Okay. The positive thing is that we don't use a lot this word with the meaning of sequence of 16 bits. Okay, since usually we use, for example, 32 bits. That is a D word, double word. Okay, but also we have a quadruple word that is a sequence of 64 bits. Okay. Here you can see another representation of the unit of information: byte, word, D word, Q word. The Q word, okay, the same. And we are going to see why it's possible to represent the byte information inside here with, for example, in this case, a number error letter. Okay. But remember this division for now: byte, word, D word, Q word. Another important element is the difference between value and representation. Okay, a numeric value, for example, the value 5, okay, can be represented in different modes. So remember, here we are discussing the difference between value and representation. Okay, for example, we use the value 5. How is possible to express the value 5? To represent the value of 5, we can use, for example, the Italian word cinque. We can use the English word 5, the word that I use to express the value inside the brackets. I use the word 5. We can use the digits, the Arab digit 5. We can use the Latin V, is another representation to express the 5 value. We can use 5 different crosses. We can use the binary representation. Okay, little spoiler, this is the binary representation. We can use the dice. We can use the finger of our hand. Okay, and many other representations. So we have a value 5, and we can express this value in different ways. The binary representation is only a just specific representation used by computers. Okay. Remember that it's important to select the binary representation since different representations have different properties. So we want to use the proper representation inside computer since different representation have different properties. That's why we are going to use specifically the binary representation. For example, what is the meaning of this sentence? If you use the Roman notation, the Latin notation, with the letter V, it's very difficult to compute multiplication, for example. You can try to do, you can see how it's possible to use the Latin representation. You can try to use the Latin representation to do some multiplication, and you will see that it's not so easy. So in this case, maybe it's better to use the decimal representation, our representation. Okay, in computer, it's better to use the binary representation. And we are going to see why. Binary representation is positive things, is a positional representation. So you know already how it's possible to use the binary representation to express values. Okay, you know how it's possible to use the binary representation, and we are going to see why. Okay, since use the decimal representation, that is the same thing, so the binary representation. We just only change only few things. Okay. Okay, so what is a positional representation? Is a numeration system in which a number, a real number, okay, is represented by these elements. First element. Let's go. For each positional representation, we have a set of different symbol S, uppercase, okay? We have a set of symbol S. The size of this set is called B, is called base, and so it is represented by the letter B and gives the names to the representation. Okay, so with the decimal representation, we have 10 different symbols. With the binary representation, we have only 2 different symbols, 0 and 1. Okay. Each symbol S in our positional representation is multiplied by with B to P. That's all the math that we are going to see together today. Yeah. So S is multiplied with B to P. S is the symbol, P is the base. The base is the number of different symbols that we have, and P is very important since P is the position. That's why we call this system positional representation, since the position is very important. So B to P, P is the position of the symbol that we are going to represent. Okay, the position, remember, and I will repeat this element many times since it's very important. We count the first position is on the right, okay, and start from 0. We are in computer science, so we start from 0 every time. Okay, so we start to count the positions from the right and from 0. 0, 1, 2, 3, 4. Okay, not 1, 2, 3, but 0, 1, 2, 3, 4, and so on. Okay, from the right to the left. So the final representation, we can group all these sentences, these 3 sentences, and we can say that the final representation is S symbol multiplied with B to P. Okay, where S is the symbol, B is the base, and P is the position. That's all. What is a positional representation is this equation. Okay, base, symbol, base, and position. With this equation, we can express the decimal positional representation, binary positional representation, and many others that we are going to see together. Question about that? Okay. Okay, we can start with the decimal positional representation. Okay, so we can understand if we have understood all the elements in the previous slide. So decimal positional representation, the representation that you use every day. Okay, I'm not sure since maybe some of you use a different representation. It's possible, but here in Europe, in Italy, every day we use the decimal positional representation. Decimal, since the base is equal to 10, we have 10 different symbols. What are these symbols? The Arab digits. Okay, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. From 0 to 9, we have 10 different symbols. So the representation is S, the symbol that we want to use, times 10, the base. Okay, B equal to 10, decimal positional representation, to the position. That's all. 253. Okay, I'm using the decimal position representation to express these values. Okay, but to show you how it's possible to use the decimal position representation to have these numbers. Okay, so we can start from the first position. In the first position, we have the digit 3. Perfect. Okay. So we start from the first position. Remember, first position is on the right and start from 0. So we can write that one. Okay. So remember, we have to write this equation. So the first element is the symbol. In this case, the symbol is 3. Okay. Times 10, decimal position representation. Power, the power is 0, the position. Okay, the position of 3 is 0. First position on the right, we start from 0. So the first element is 3 times 10 to 0. Second element, 5. This one. Symbol 5 times 10, decimal position representation, to second position is the number 1. 0, 1. So final representation is 5 times 10 to 1. We group all these representation with the sum, okay? Of course, since we have to add all these components to obtain the final value. The final digit is the final, the last digit is 2. So what we can write here, 2, the symbol, times 10 to third position, 2. Remember, what 0, 1, 2, 3, 4 correspond to first position, second position, third position, fourth, 5, and so on. Okay. Second example here, the attention, since we have the point, is not a problem. You have only to remember that the first position is the position on the right before the point. Okay, and everything is similar. So here in this case, the first position is here. Okay, the most right position before the point. So 3. What we can say with what we can write here, 3 times 10 to first position 0. Second, 2. 2 times 10 to second position 1. Okay. Okay, now we have the digit after the point. In the position after the point, remember that after the decimal point, the first position is -1. Then we have -2, -3, -4. Okay. So we have 0, 1, 2, 3, dot point, okay, point, decimal point, -1, -2, -3, -4. Okay, so in the first position, after the decimal point, we have the symbol 4 times 10 to the position. The position is -1. Second number, second digit, 7. Second position after the decimal point. So we will write 7 times 10 to -2. Okay, easy peasy. So first element is 2 times 10. Oh, I forgot in the previous example to do all the computation, but it's pretty simple. Okay, we multiply all the elements, we sum all the elements, and we obtain the final value that correspond to the initial value. Since we are going only to see the use of the decimal representation to express numbers, values in the decimal representation. Okay. In this case, so we have 20, then here we have 3, and here remember maybe from your high school that -1, you can write -1, the power of -1 has 1/10. Maybe you remember something about, okay, -2 is 1/10 to 2. So 1/100 is only math, okay? So here we have 4 times 1/10, that is 0.4, and 7 times 1/100, that is 0.07. If you do sum, you obtain 23.47 initial value. That's all. Well, we have used the decimal representation, positional representation, to express numbers, values in a decimal positional representation. Okay. A very simple example, just to understand how it's possible to use the positional representation to express values. Doubts? Questions? Since now we are going to see some properties about the positional representation. We have only 2 properties about positional representation, and they are very simple. So if we have key digits, what's the meaning of key digits? Is the number of position that we can use to represent a value, okay? We have 3 spaces, okay? In these 3 positions, we can put a symbol, okay? For example, if I put with the decimal position representation the number, the digit 104, I obtain the number 104. Why? From the previous slide. So what we can say about the use of, for example, key position? Okay, the number of these different positions, the number is the letter key, lowercase, okay? So with key different position, the max value that we can obtain is B to key -1. Since if we have only 3 positions, what is the maximum number that we can write? 9, 9, 9. Is them okay from empirical point of view? And in this case, B to key -1 is the following: 10 to 3. Okay, 10 since is the base. We are in the decimal. We are using the decimal positional representation. B is the base. 3 is the number of positions that we can use. And then we have to remember that we start from 0. So we have to write -1. Okay, so the maximum value is 999. And second rule, so the first is this one. The second is that the maximum number of different representations is B to key. Since in 3 different positions, we can write all the representation that range from 0 to 999. And if you count them, you can find that we have 1,000 different representation. 1,000 is 10 to 3. Okay, so remember only B to key -1 and B to key. They are very 2 important properties, since we are going to use these 2 properties with the binary representation. Okay, with the decimal positional representation is quite intuitive to use these properties. With the binary digital representation, maybe it's more complex, so it's important to understand these properties with the decimal positional representation. Questions? No. Okay. So we are ready to see together the binary positional representation. Okay, so binary positional representation, binary. So the base is equal to 2, only 2 symbols. What are these 2 symbols? 0 and 1. Okay, So the final representation, we can express the final representation, the value with S or 0 or 1, multiply with the base 2, binary position representation to the position. So if you see this number, 0, 1, 1, 1, okay? In this case, what we can do? the same steps that we have done before with the decimal positional representation. We start from the first digit, the first 1. So what we can write, 1 times 2 to first position 0. Then we have the second one, so 1 times 2 to 1, second position. Then we have the third one, so we have 1 times 2 to 2. And finally, we have the 0, so 0 times 2 to 3. So here we have the 0, so a multiplication with 0 is always 0. We have here 1 times 4, 1 times 2, 1 times 1, and so the final result is 7. So using the binary positional representation to represent the number 7 in the decimal positional representation, the result is that 7 is 0, 1, 1, 1. Okay, that's all. That's all the binary positional representation that you can see in computer science. Okay. Now you are able to use the binary positional representation to discuss with someone to, I don't know what kind of topic. We can also simplify, okay, all these steps, since we can omit the 0 number, since the results of the multiplication with a 0 is always 0. So if we see that there is a 0, we can omit to write 0 times, we can omit all the details. We can also omit the 1, since the 1 doesn't modify the results of the multiplication, okay? Since 1 times 2 is 2, 1 times 1, 1, 1 times 4 is 4. So we can omit also the part about 1 times. We can omit this part. And so, as you can see here, the final, all the steps that we have to follow to use the binary positional representation are very simplified, since, for example, with the number 1001, note the difference. I don't say 1001, since it's not a decimal number, okay? In the decimal positional representation, I should say 1001. With the binary positional representation is the number 1001, okay? So with the number 1001, what we have? We can skip all the zeros, not important. We start from the first one. So first one is in the first position. We can omit also 1 times, since the 1 doesn't modify the results. So we have only to write the power of 2, the related power of 2. That is the power of 2 related to the position of the digit. So first one is 2 to 0, since the 1 is the first position. Then we have 0 position, 1, 2, 3. The fourth position is the number 3. And so here we have 2 to 3. That's all. 2 to 3 is 8. 2 to 0 is 1. Remember, any number to 0 is 1. Okay. And so the final result is 9. So it's possible to represent the 9 value with the decimal position representation through the 1001 with the binary position representation. Yes. There is not a translation. We directly use, in the machine language and in the assembly, we directly use the binary values. Okay. Since a computer thinks in binary code, not in decimals. Okay, there is a translation, of course, but at the base level, the computers work only with binary representation. First computers didn't work with binary representation, for example, used maybe the decimal positional representation, the octal positional representation with other representation, okay? Only modern computer use directly the binary positional representation at low level, okay? At high level, we use decimal positional representation, and then this representation is translated in the other lower levels. That's okay? Other questions? We can apply the very same properties that we have seen for the decimal positional representation, also for the binary positional representation. So the maximum value is b to key minus 1, and the maximum number of different representation is b to key, if we can use only key position. So if we have only key digits. Also, in this case, we have 3 digits, so 3 possible positions that we can use. So remember here, the base is 2, binary positional representation. So the maximum value is b to key minus 1, b2, key 3, minus 1, 8 minus 1, 7. The maximum number that we can represent with 3 different positions is 7. 1, 1, 1. Okay. 2 to 0, 2 to 1, 2 to 2. 4 plus 2 plus 1. 7. While the maximum number of representations, different representation, is 8, since we start from 0, 0, 0, and we go to 1, 1, 1. Okay, if you change every bit of information, you can find finally 8 different representations. Okay. Are you ready to see also other positional representation? Since now we have understood the base element about the representation, and now we are able to maybe understand also other different representation. Maybe we can have a little break now, 5 minutes, not more. So you can think about the binary positional representation, then we can discuss the other positional representation, okay? We are going to apply the same formula, the same equation, S times B to P, okay? We change only the base. That's all. See you in 5 minutes. Maybe you can open also, can you open also some windows if they are not broken? I don't know.
Il concetto che domani vengono risposte più o meno così per la, diciamo, per convertire in base 10, più o meno così. Processo.
Sì, quello che ho spiegato, come appunto vedremo nelle slide dopo, è uno dei modi per convertire numeri binari in base 10.
Invece guardavo per...
È già andato
no, ma
avanti.
vabbè, cercavo solo di capire la logica, quindi ho visto c'è negli esercizi. Invece per la conversione da 10 in base 2, se c'è il resto...
Bisogna fare la tabellina che c'è sopra.
Ah, ok.
Questa qua. Adesso comunque la faccio vedere. Okay. Conviene disegnare quella e poi prendere l'ordine. Okay. È più, all'inizio almeno è più chiaro.
Perfetto, grazie.
Some people don't want for or you think
Okay, I hope that you have reflected about the binary representation. Now we are introducing other conditional representation, okay? The positive thing is that we don't have to add anything since we have all the tools, all the knowledge to introduce other positional representation. Okay. The only thing is to be noted is that we add a subscript to indicate the base used. Since if I write, for example, the number 1, this number, and without using my voice, you don't know if is a decimal, is this value is represented through the decimal position representation or the binary representation. Okay, if I say 1001, maybe you can think about decimal, or 1001 is the binary. Okay, So that's why usually we use a subscript to indicate the base that we use to represent the value. Okay, so if I write here a 2, I'm using the binary representation. So 1001. If I write here 10, I'm using the decimal positional representation. If I write 8, I'm using the octal positional representation. That is the new representation that we are going to see together. Okay. The octal positional representation, octal meaning 8. So we have 8 different symbols. B is the base, B is equal to 8. So here you can see the list of symbols, 8 symbols. So we have the Arab numbers starting from 0 to 7. 0, 1, 2, 3, 4, 5, 6, 7. Okay, Arab numbers for the octal positional representation. So the representation, remember the formula S times B to P, S times 8 to P, where S is the symbol, one of the symbol, and P is the position. So if I write the number 7, 2, 1 with the subscript equal to 8, so we are using the octal positional representation. What is the meaning of this number in the decimal positional representation? Okay, first one is 1 times 8 to 0, first position. Then we have 2, 2 times 8 to 1, second position. And then 7 times 8 to 2, third position. We can add all the results and we obtained 465 in the decimal positional representation. Okay, so the meaning of this number, the value of this number in the decimal representation, positional representation, is that one. Hexadecimal positional representation, also abbreviated with X, okay? We are going to use a positional representation in which we have 16 different symbols. So the B is equal to 16. And there is a specific reason, okay, to use the hexapositional representation. I'm not mad, okay? I'm introducing the hexadecimal representation since it's very important for the binary representation, as in the following, we are going to see in the following slide. Here we have a problem. We have 16 different symbols, but Arab numbers are only 10. So the first 10 position in the first 10 symbols are represented by the numbers, Arab numbers, 0, 1, 2, 3, 4, 5. But we have other 6 positions to cover. We don't have any other Arab numbers, so one solution is to use letters, okay? Alphabetical letters. So A, B, C, D, E, F. So the set of the symbols used with the hexadecimal positional representation start from 0 and goes until F. So in this particular positional representation, the numbers, the values are represented both with letters and number, okay? Maybe it's a little weird, but it's just another representation. So with the hexadecimal positional representation, we can have a number expressed represented in this way, 7D1, 16, since we are using the hexadecimal positional representation. Okay, so we have also letters in the numbers, 7D1. What's the meaning? 1 times base 16 to 0, first position. D, okay, the value of D is that A, the value of A is 10, B is 11, 12, 14, 13, 14, 15. F, okay. So the value of D is 13. So we have to write 13 times 16 to 1, and then 7 times 16 to 2. Can do all the computation. You can see that the final number is in the decimal positional representation is 2001. With fewer digits, with the hexadecimal representation, we can express a number that in the decimal representation have more digits. Okay.
If I want to express 2 in a decimal, how do I do it?
We are going to see how it's possible to convert the base number in the last line, okay? And I'm thinking about to introduce this now or maybe later, since I don't want to. I would like to simplify the concept, not to put a lot of elements. Well, the number 2 is 2 times 16 to 0, okay? But it's not so easy to understand here how it's possible to have different base conversion. So we are introducing these elements. Okay. So we repeat some important element about hexadecimal representation. We have 16 different symbols. Symbols range from 0 to 9 and also from A to F, okay? Usually we use uppercase letters, but we can use also lowercase letters to represent values from 10 to 15. So 0, 9, 10 to 15 with the letters. And why we have introduced the hexadecimal representation? This is why, very important. Since we can use the hexadecimal representation to express binary numbers in a more compact way. Okay, it's very important to express also the binary number in a very compact way, and we are going to see how it's possible to do that. Okay, in the following slides. So, how it's possible to convert binary numbers in also decimal numbers in hexadecimal. You can see here this table. In this table, we have the first column that is the hexadecimal representation. Here, the subscript is not the 16, but is the X abbreviation. Okay, it's the same. In the second column, we have the decimal representation. Also, in this case, we don't have 10, but that has decimal representation. And we have also the octal representation. And finally, the last 4 columns are for the binary representation. As you can see here, the binary representation occupies a lot of space. Okay, for example, with the letter F, so with only 1 digit, we can express the same value of 15 in the decimal representation. The value that is expressed by the use of 4 different 1. So you can see that here to express 15, we use 2 digits in decimal position representation, 2 digits for the octal position representation. Unfortunately, 4 digits for the binary position representation, only 1 digit with the hexadecimal position representation. So, as you can see here, it's possible to use the hexadecimal representation to express in a more compact way all the binary numbers. Passing from binary to hexadecimal to binary is very simple, and we are going to see later, but you can assume that is very simple, so it's not a very complex operation. Then we can use in a very easy form the hexadecimal representation to see the number, okay, and to see the value of the binary representation. Okay, I'm seeing that all the details. I have explained all the details about this slide, and maybe you're also about your answer. You can see here the conversion. It's quite easy since we have 2 in hexadecimal representation, but we are going to see 1. Okay, but 2 is multiplied with 16 to 0, so 2 times 1 is 2. Okay, with the binary representation, we have 0, 0, 1, 0. Why? First position 2 to 0, discard. Second position 2 to 1, 2. Perfect. So the final representation is 0, 0, 1, 0. Okay. 15 or F is the maximum value that we can represent with 4 digits. Maybe you remember the formula: B to K minus 1, B 2 to key 1, 2, 3, 4. 2 to 4 is, I don't know, 16. Perfect. Okay. Are you still alive? You are alive? Okay. So 16 minus 1, the maximum value is 15. Perfect. The maximum number of different representation is 16. D to key. Okay. I think that we have finished. Yeah. Okay, that's about questions about octal hexadecimal representation. Okay, so we have seen together decimal positional representation, binary positional representation, octal and hexadecimal positional representation. We have introduced the hexadecimal positional representation since we can use this representation to express binary numbers in a more compact way. Okay. Positional representation is a very powerful tool from a general point of view. Before the positional representation, for example, here in Europe, we use the system, the latent system, okay, based on some of different addiction of different values, okay. We have the number 3 with 3 in this way, since we have 1, 1, 1. So we have the number 3, okay. We have the number 4. Have you ever seen the latent system? Maybe some, okay. So, for example, here we have the number 4, since we have to do 5 minus 1, okay. But if we put this element on the other sides, we have the number 6, okay. It's a completely different way to represent values. Nowadays, and also with computer, we use the positional representation in which we use S to multiply with B to P. That is different from the latent system. Okay, so base conversion. Now we are ready to convert from base 2 to base 10 to from base 10 to base 2, from base 16 to base 10, and so on. Okay, are you ready to do that? I think yes, but okay, it's quite late, so we are trying to do that. So how is possible to pass from base 2 to base 10? We can apply the method that I showed you before, so nothing new. We have the number in base 2, 1, 0, 1, 1, 1. We can apply the same procedure that I showed you before, okay? So we take the first one, 2 to 0, the second one, 2 to 1, 2 to 2, and the 0, 2 to 3. Remember, you can omit all these details, and then we can write directly 2 to 0 is 1, 2 to 1 is 2, 2 to 2 is 4, and here we have the 0, and here we have 16. So the final result is 23. So the number 10111 corresponds to the number 23 in the decimal positional representation. So we are passing from base 2 to base 10. Remember that, okay, I already told you that we can omit all the 1 and the 0. So if you have this number, you can only write 2 to 0, 2 to 2, 5, 6, and so 64 plus 32, 4, 1, and here the final result is 101 with the decimal position representation. And you can see also the importance to use the subscript, since this number can be, for example, a binary number, can be also an octal number or an hexadecimal number, okay? Another important element to note is that you have to know what to do this conversion, the powers of 2, since the conversion from base 2 to base 10 is based only on the power of 2. That's all. So you have to know very well the power of 2. I report here a slide taken from Wikipedia of the power of 2. And I think that in our exercise, the best option is to know the power of 2 until 2 to 9. Okay, but also 2 to 10, maybe. Okay, it's not so difficult. So we have 1, 2, 4, 8, 16. 32, 64, 128, 255, 56, sorry, and 512. Okay. All the other, you can see that we can express a lot of values in there. Okay. This slide is very important since you have to remember that with the binary system, we use the power of 2 that are different from the power of 10 that we use in the our decimal position representation. Okay, so here you can see bit is expressed with the lowercase letter b. If I use the lowercase letter b, I mean bit. Okay, and so how many bits we have? 1. How many bytes? Less than 1, so 1/8. Okay, since you know that in a byte we have 8 different bits. Then we have bytes, a set of 8 different bits. We express byte with the uppercase B. It's very important, remember. So if you use the letter B, I mean byte. How many bits we have in 1 byte? 8. How many bytes? 1. Okay. Okay. Here we use the same prefix that you use also in the decimal position representation. So the prefix kilo, mega, giga, or giga, terabytes, and so on. Okay, but we apply this prefix with the bytes. Okay, not the decimal number. So in this case, we have kilobytes. We express kilobyte with the key B. Put attention, key is lowercase. Okay, key B is not uppercase. Okay, when you write kilometers, kilogram, you must use the key in lowercase. Okay, please. We are not using Kelvin, but kilo. Okay, Kelvin are expressed with the uppercase key. Okay, so if you use the key in uppercase is Kelvin, if you use key in lowercase is kilo. Okay, the meaning is 10 to 3, 1000. Okay. So kilobyte is key B. Then we have megabytes, gigabytes, terabyte, 2 to 10, 2 to 20, 30, 40. Okay. Remember that we are using the power of 2. So 1 kilobyte corresponds to 1024 bytes. Okay. Maybe you recall the decimal positional system in which kilo is 1000, but with the power of 2, we have different values. Okay, in this case, 1 kilobyte is 1024. Okay, that's why when you buy an USB pen, you can see maybe the 8 gigabytes, you plug your key and you can see another number, not 8,000 or 8,000 bytes, but another number. Okay, why? Since here we are using the power of 2, okay, not the power of 10. Remember this element. Okay, first assignment of today. We can try to do this exercise now, and then we can try to do this exercise together in 5 minutes. Okay, you can try to do that. It's not so. Remember, we want to convert this number from base 2 to base 10. You have to start from the right. You have to count the position starting from 0, and then you can write the power of 2 related to the position of the 1. Okay. You can start, and I give you a few minutes since it's late, so I will show you the solution that is in the following slide. If you don't have any idea about to do this exercise, please tell me. Since at this point, I assume that you know how to do this exercise, okay? So you know that you have to take the first one, multiply the first one, the 2 to 0, and so on, okay? When you have done with the first two numbers, we can, I can show you the solution. Have you done? Okay. Then you can continue this exercise at home, but okay. The answer is 10 for the first number. So here we have the position 0, 1, 2, 3. So here we have 2 to 3 plus 2 to 1. So 8 plus 2, so 10. Okay. Second position is the same. Note that in the last position, we have 1, 1, 1, 1, 1. So 5 different ones. The result is 31. That is the maximum value that we can obtain with 5 bits, 5 digits, since we have to apply 2 to 5 minus 1. 32 minus 1 is 31, okay? And for example, in this case, you don't have to do anything since you have only to count the position 1, 2, 3, 4, 5. So 4. So 2 to 4 is 16. So you can obtain the decimal representation starting from binary numbers in a very straightforward way. Okay, questions? So we can move forward. Now is the turn of from base 10 to base 2. Okay, we have seen base 2 to base 10. Now base 10 to base 2. Here the conversion is pretty simple since the idea behind everything is that we have to find the power of 2 inside the number that we want to convert. Okay, how is possible to find the power of 2 inside the number? We can apply a sequence of division by 2. And then we can take the inverse sequence of the reminders to have the final representation. For example, the example is more easy than the sentence. We want to convert this number 13 from base 10 to base 2. So I write here 13. Then I draw this table. Okay, I don't have enough space, but I'm starting to draw this table. And then I say, okay, I apply the first division by 2. I write here the results and here the remainder. Okay, so 13 divided by 2 is 6 and 1 of remainder. Then I draw another line and then I repeat the same procedure with the 6, the new number. Okay, 6 divided by 2 is 3 and that's all. So no reminders, 0. Then 3 divided by 2 is 1 and 1 reminder, of course. And when you achieve the 1, the last one is the final step, since in the final step we have 1 divided by 2 is 0 and the remainder is 1, of course. Okay, with the 0 we stop our computation. Remember that the final representation is given by the inverse order, inverse sequence. So we start from right to the left. So the final representation 13 base 10 is equal to 1, 1, 0, 1 in base 2. Remember this error. A lot of errors in the final exam are due you forgot to take the inverse order. Okay, you have to flip the reminders that you obtain in the bottom part of the table. Okay, so remember, you must invert the order of the reminders for the binary, for the final binary. Also, in this case, we can do a very little assignment. Maybe we can do only the first two numbers, okay? And I give you 3-4 minutes to do that, okay? So you can write here in the blank part the table, so you can start 15, and then you can draw the table. Divide by 2 is 7, and then 1, okay? Try with the first two, 15 and 32. With the 32, there is a escamotage in French, okay? Also with the first one, there is an escamotage, but we are going to see together why. Okay, so here you can see the solutions. In this case, 15 is 1, 1, 1, 1. Okay, you can compute 1, 1, 1, 1 with the table. So you can write 15 divided by 2, 7. Reminder 1. 7 divided by 2 is 3. Reminder 1. 3 is 1. Reminder 1. 1 is 0. Reminder 1. 4 different ones. The other way is to say, okay, 15 is the maximum value that we can express with 4 different bits. So if it is the maximum value, we can write 1, 1, 1, 1. That's all. For the second, we have 32, so we can apply the table. Also in this case, 32 divided by 2 is 16, remainder 0, 8, remainder 0, 4, remainder 0, 2, remainder 0, and so on. In this case, we can also, but we can also think that the fact that 32 is a power of 2, okay? And in particular, I can write only the one that corresponds to the related power of 2. In this case, 0, 1, 2, 3, 4, 5, okay? Since I know that 32 is 2 to 5, so I can write a number that in which the 1 is in the 5th position, okay? Another 1, 0, 1, 2, 3, 4, 5, okay. 6th position, but starting from 0, okay, is 2 to 5. We can apply the same techniques with 64, 128, since they are power of 2. But you are forced to use the method that I showed you before with the number, for example, 45 or 93, since in this case we don't have power of 2. Okay. If you are not sure about, I suggest you to use the table method. Okay, is quite simple and you obtain a very good results in a very sure form. Okay. Here you can see some binary numbers. Maybe you can try to obtain, starting from the decimal number in the first column, the equivalent binary number. So you can see that 0 and 1, we can express the number 0 and 1 with only 1 digit. Then we use 2 digit, then 3, 4, 5, okay, with the increasing amount of the number. Hexadecimal conversion. There is a trick. There are 2 approaches, and there is also a trick. Okay. For example, we can use the base conversion, the same base conversion that we have seen together with the base from the conversion from base 2 to base 10, as multiplied by p to p. Okay, so we can use the same approach. So in this case, the number is 240 with this first element example. We pass from the decimal representation, and then we convert the decimal representation in this hexadecimal representation using the table divided by 16. But the other way to convert numbers, the more easier way to convert numbers, is to divide the binary numbers in group of 4 digits, and then we can convert the group of 4 digits using the letters or the numbers in the hexadecimal representation. You have only to recall the table that I showed you before, in which, for example, the number 0 is the number 0 in the hexadecimal representation. The number 1111 is the letter F. Okay, the previous number is the letter E, and so on. Okay, you have to remember this table. Okay, you divide the binary number in group of 4, and then you can remember this table to do the conversion. Okay, so you can see that the use of hexadecimal representation is quite simple. And maybe you can understand also why I show you this representation. Okay, so a byte, this is an example, okay, but a byte, in the byte I have 8 different bits. 6. I divided bits into two groups. Oh no. Okay, well. And in the first group, I put, for example, in this example, I have the letter D, and the last group is the number 5 with the hexadecimal representation. So I can represent a byte of information using 2 different digits in the hexadecimal representation. So with a word 16 bits, I can use 4 digits. For a keyword, I can use this amount of 1, 2, 1, 2, 3, 4, 5, 6, 7, 8, 16 digits in the hexadecimal representation. Okay, so now you are able also to understand this figure that I showed you in the first part of the slide of today. What else? We have finished. Okay, maybe what do you prefer? Doing these 2 slides now or next time? Next time. Okay, you are free. We have finished. If you have questions, we can discuss something, or we have finished the lesson today.